Welcome back to the deep dive. We have a stack of papers today that, honestly, when I first looked at the titles, I thought this might be a mistake. Or maybe even a prank.
Have the same reaction.
Because we are looking at sources that are effectively auditing the most famous equation in human history.
It does feel a bit like walking into a cathedral and starting to question the architecture, doesn't it?
Yeah.
I mean, we were talking about the bedrock.
Exactly. We're talking about E equals mc squared, Albert Einstein, the equation that is on, T-shirts, coffee mugs, mouse pads.
The few ill-advised tattoos, I'm sure.
Probably a few of those, yeah. It is the absolute gold standard of modern physics. It tells us that energy and mass are, well, essentially the same thing, just in different states of dress, convertible by the speed of light squared.
It's elegant. It's beautiful.
And for the last 100 years, it has been the absolute law of the land.
It is the law. And to be clear, right from the start, because I don't want anyone rage quitting this deep dive in the first 2 minutes.
A very real possibility.
The papers we're analyzing today, specifically the Steelman, structured vacuum, and the volumetric rest energy ansatz, they are not saying the law is wrong.
Okay, good.
They aren't saying Einstein failed math class or anything like that.
Right, so just to set the table here,
Yeah,
we aren't canceling Einstein today.
not at all. Einstein is safe. But these sources argue something arguably more interesting and perhaps a lot more subtle. They argue that E equals mc squared is a special case.
A special case.
Yeah. They claim it represents what mathematicians call the asymptotic limit.
Asymptotic limit. Okay, that's a heavy phrase to throw out this early. Can you break that down for the listener who, hasn't touched calculus since high school?
Sure, think of it as the boring baseline,
Huh?
or maybe the default setting. The argument is that Einstein's equation is perfectly true if, and it's a very big if, the universe is empty, infinite, and really far away from any walls.
Okay.
It describes energy in a vacuum that is completely featureless. It basically assumes the stage on which physics happens is just nothing, a void.
But the real universe isn't a featureless void.
Never. The moment you introduce walls or cavities or any kind of specific geometry, the equation needs an update, needs a little asterisk next to it.
So the mission of this deep dive, then, is to explore what happens when the universe isn't empty and boring. We are looking at a concept the sources call the spectral constraint principle.
That's the one.
And the core hook, if I understood the abstract correctly, is that energy isn't just a number floating in the ether. It's a consequence of the space it lives in.
That is the Blinkist summary right there.
Yeah.
Energy is a spectral consequence of constraint.
Which sounds poetic, almost philosophical, but let's get concrete. It
Yeah.
means if I change the shape of the container, I change the energy of the thing inside the container.
Precisely. And not just in a, chemical way, but in a fundamental rest energy sort of way.
Yeah.
The sources argue that this is simply honest accounting.
Honest accounting, I like that phrase.
Me too. They believe that for a century, physics has been treating geometry like it's just the background stage scenery. It's just where the play happens.
Right, it's decorative.
But these papers argue that geometry is actually one of the actors. It's causal. It's driving the plot.
And we are definitely going to get to the controversy later. The smackdown section of our notes is extensive because obviously you can't just tweak E equals mc squared without inviting some very, very heated criticism.
Oh, the objections are fierce. As they should be. This is a big claim.
And the papers actually steelman those objections, which I appreciate. They don't hide from the fight. They run towards it.
Which is good science. You have to anticipate the critique.
But before we get to the fight, we need to understand the weapon. We need to really understand what this spectral constraint principle actually is. The authors use a metaphor that I found incredibly helpful to visualize this. They talk about a choir.
Yes, the choir metaphor. It is essential for understanding what we mean by spectral. Because spectral is a word that, it scares people. It sounds like ghosts or something.
Or James Bond villains.
Yeah.
Spectre.
Right, exactly. But here, spectral just refers to a spectrum, a range of frequencies, a collection of waves.
So lay it out for us. How does a choir explain nuclear physics?
Well, think about what energy actually is at a quantum level. It's not a solid brick. It's not a billiard ball. It's a collection of waves, fluctuations.
Okay.
In this metaphor, think of energy not as a single object, but as a chord being sung by a massive choir, a huge one. That chord is made up of thousands and thousands of individual notes or frequencies. In physics, we call these modes.
Okay. So the energy of a system is the sum total of all the notes being sung by the choir at that specific moment.
Correct. Now let's set the scene. Imagine that choir is standing in the middle of a massive open field, a prairie in Nebraska. There are no walls, no ceiling, just open sky. The acoustics are perfectly flat.
Total freedom.
Total freedom. They can sing any note they want. A deep, rumbling bass, a piercing high soprano. The sound waves just travel outward forever. They're not constrained.
And that's the unconstrained universe. That's Einstein's vacuum.
Exactly. That is the asymptotic limit we talked about. Infinite space, no barriers. But now, take that same choir and shove them into a small tiled bathroom,
Oh, I can already hear that.
or a long, narrow tunnel, or a giant cathedral. What happens to the sound?
It changes completely. It echoes, it resonates. Certain notes get really, really loud and others just disappear.
It does. But more specifically, the room decides which notes are allowed to exist. If the room is very small, a low-frequency bass note, which physically has a very long wavelength, might not even fit inside the room.
It just can't form.
It gets suppressed. It's like trying to fit a semi-truck into a one-car garage. It just doesn't go. Conversely, certain high notes might bounce off the walls, interfere constructively, and just boom, they amplify. The geometry of the room rewrites the repertoire of the choir.
I see exactly where this is going. So the sound, which represents the energy, is totally distinct in the bathroom versus the open field, even if it's the exact same people singing.
Exactly. The source argues that energy, E, is always the result of this negotiation between the choir, the vacuum modes, and the room, the geometry. You cannot separate the singer from the acoustics of the hall.
So the logic chain, and I want to make sure I have this locked in, is the constraints, which are the walls, determine the spectrum, which are the notes. And the spectrum then determines the energy distribution.
Constraints, arrow, spectrum, arrow, energy. That is the fundamental loop. If you understand that, you basically understand the core thesis of all these papers. Everything else is just the math to prove that loop exists.
And the bar, which you mentioned earlier, whether that's a physical wall, a gravitational field, or a conducting plate, that's the boundary condition.
That's the thing that tells the choir what it's allowed to sing. It's the conductor, in a way.
You mentioned the bar. In the papers, they make a really interesting pivot here to explain this concept using something much more tangible than quantum modes. They talk about cooking,
Yes.
specifically boiling water.
I love this example because it bridges the gap between, high concepts quantum field theory and your kitchen. It's a proof by real-world demonstration. It shows that we already accept this principle in thermodynamics.
We just haven't connected the dots.
We just haven't applied it to mass energy yet.
So let's walk through the thermodynamics here, because I think most of us take boiling for granted. You put the pot on the stove, you wait for bubbles, you throw in the pasta, done.
We do. If I ask you, at what temperature does water boil, what do you say?
100 degrees Celsius. Or 212 Fahrenheit. That's the definition. That's what they teach you in 3rd grade.
Right. But that answer is incomplete. It's actually wrong. Or at least it's missing a crucial piece of information.
What's it missing?
It's the answer at 1 bar of pressure, which is the average atmospheric pressure at sea level. We take the 1 bar environment for granted because we live in it. It's our free space.
It's our open field.
It's our open field for water molecules. But let's move the kitchen. Let's take a stove and a pot of water to the top of Mount Everest.
Okay. We're at 29,000 feet. The air is thin. The pressure is, what, roughly 0.33 bar?
Correct. About a third of the pressure at sea level. Now, you put your pot on the stove, you heat the water. What happens?
It boils at a much lower temperature. It's around 70 or 71 degrees Celsius, I think.
Roughly 71 degrees, yes. And this is a very practical problem for mountaineers. If you try to cook pasta at 71 degrees, it's going to be a disaster.
Why? I mean, it's boiling. It's bubbling.
The water is bubbling. It looks like it's boiling, but it doesn't have enough thermal energy to properly break down the starches. You get crunchy pasta.
Crunchy pasta on Everest. That's a sad image.
A very sad image. But explain the why. Why does it boil sooner?
Because boiling isn't just about heat. It's a war. It's a war between the vapopressure of the water molecules trying to escape into the air and the atmospheric pressure pushing them back down into the pot.
The atmosphere is the lid on the pot.
Exactly. The atmosphere is the constraint. And on Everest, the lid is much, much lighter. The push is weaker. So the molecules can escape, they can boil, with much less energy. The energy threshold for the phase change has been lowered by the environment.
It's been rewritten.
Now let's go the other way. Let's go to the bottom of the ocean.
The Mariana Trench. Or, if you don't have a submarine, just a heavy-duty pressure cooker works too.
Yeah.
If you go, say, 500 meters down, the pressure is 50 bar. 50 times the weight of the atmosphere.
That's a heavy lid.
A very heavy lid. In that environment, you can heat water to 150 degrees Celsius way hotter than normal boiling, And it will stay perfectly liquid. It will not boil, not a single bubble.
So here's the philosophical question the papers ask, and I want the listener to really chew on this. Did the water change? Was it different water on Everest than in the deep sea?
And the answer is clearly no. It is the exact same H2O molecules, hydrogen, oxygen. The chemical bonds haven't changed. The intermolecular forces, the van der Waals forces, are the same. The water is identical.
So why did the energy threshold for the phase change, the boiling point move all over the map?
Because the constraint changed. The environment changed. The bar rewrote the energy ledger for that water.
This is the aha moment for me. We usually list boiling point as a property of water, like it's intrinsic to the molecule, like it's atomic weight or something.
Right, like it's a permanent feature.
But it's not. It's a property of the water in a specific context.
Context is everything. The choir of thermodynamic options available to that water molecule is different on Everest than it is in the deep ocean. The geometry of the pressure environment dictates the energy ledger.
And the source takes this one step further to connect it directly to gravity, because what creates that atmospheric pressure in the first place, it's not magic.
It's gravity.
Yeah.
Gravity pulling on the entire column of air above you. And what is gravity, according to general relativity?
It's the curvature of space-time. It's geometry.
So the logic holds. Gravity, which is geometry, creates the pressure gradient, which is the constraint, which sets the boiling point, which is the energy threshold.
Geometry is causal. That was the phrase in the structured vacuum paper that really stuck with me. The shape of the gravitational well determines the thermodynamics of the pot of water sitting inside it.
Precisely. Now, this is where the papers ask the listener and the scientific community to take a leap. And it's a big leap, admittedly.
A huge leap.
We accept this logic for water. We accept that the bar changes the rules for matter phases. But does this apply to empty space? Does the vacuum itself behave like a fluid that can be pressurized?
And this brings us to section 2. The bridge. Because usually we think of the vacuum as, well, nothing. It's the absence of stuff. It doesn't have pressure. It doesn't have a boiling point. If I take a box of nothing and compress it, it's still just a box of nothing, right?
That is the common intuition. But it's a deeply ingrained misconception. We treat the vacuum as an inert backdrop, a stage where the actors, the particles, move around. But quantum field theory has taught us for decades that the vacuum is alive. It is seething with activity.
You're talking about the quantum foam.
Right. Virtual particles popping in and out of existence, fluctuations in the electromagnetic field. The vacuum has its own choir of electromagnetic modes, and it creates a pressure. We call it zero-point energy.
And the source argues that the Casimir effect is the direct bridge between the boiling water analogy and vacuum physics.
It's the perfect bridge.
The Casimir effect. I remember hearing about this in sci-fi, usually involving wormholes or some kind of exotic propulsion. But this is a real measurable thing, not just a theory, right?
Oh, absolutely. It was predicted by Hendrik Casimir back in 1948. It took a long time to measure it accurately because the forces are incredibly tiny, but it was definitively measured in the 90s. It's a standard feature of quantum mechanics now. You can't do nanotechnology without accounting for it.
For those who might have skipped that day in physics class or who just know the name, walk us through the setup. How on earth do you measure the pressure of nothing?
It's surprisingly simple in its design, though incredibly hard to build with the right precision. You take two metal plates, perfectly smooth conducting mirrors, effectively. You place them in a perfect vacuum, extremely close together.
How close?
I'm talking nanometers apart, a fraction of a human hair's width.
Okay. 2 plates, face to face, in the dark, in a vacuum. Nothing between them but empty space.
Now, those plates act as a constraint, just like the walls of the tiled bathroom we talked about for the choir. Outside the plates, the vacuum choir can sing any note it wants. The electromagnetic waves can be any length-long radio waves, short gamma rays, the whole spectrum.
But between the plates?
Between the plates, the waves have to fit. They have to resonate perfectly. Technically, they have to satisfy boundary conditions where the electric field goes to zero at the surface of the plate.
Okay, so like a guitar string tied down at both ends.
Perfect analogy. If a wave is longer than the gap between the plates, it's forbidden. It's excluded from the choir. It literally can't exist in that space.
So the choir inside the gap is missing its bass section. It's missing the baritones. It's just the sopranos and the tenors.
Exactly. The mode density, the number of allowed notes, is significantly lower inside the gap than it is outside the gap.
So you have a situation where there is more vacuum activity outside pushing in and less vacuum activity inside pushing out.
And that creates an imbalance, a net pressure gradient. The plates are physically pushed together by the vacuum itself.
That blows my mind every single time I hear it. Empty space pushing metal plates together just because of geometry. It's not magnetism, it's not gravity.
It's spectral exclusion. And the source makes a huge deal about the same skeleton argument here. They argue that physicists tend to treat the boiling water example and the Casimir effect as two totally different things.
Right, they live in different textbooks.
One is thermodynamics, which is heat and matter. The other is quantum electrodynamics, which is fields and vacuum. Totally separate departments.
But structurally, they are identical.
Yes. In the atmosphere, a pressure constraint rewrites matter's mode behavior. That's boiling. In the Casimir effect, a boundary constraint rewrites the vacuum's mode density. It's the same skeleton.
There's a quote in the text that I really liked. Unification is not sameness, it is common structure across distinct regimes.
It's a powerful line, isn't it?
Mm.
It's saying that if you accept that pressure changes boiling points, you have already accepted the fundamental mechanism for the spectral construct principle. You just haven't applied it to rest energy yet.
You're just in denial about the scope of the law. You think it stops at the water's edge, but the theory says it goes all the way down to the vacuum.
Exactly. You're treating them as separate phenomena, but they are expressions of the same underlying law. Constraint writes the choir writes the energy.
Okay, so we've established the foundation and we have the bridge. We know water behaves differently under pressure, and we know the vacuum behaves differently between plates. Now we have to look at the actual proposal, the new math.
Here we go.
The sources introduce a symbol that defines this entire theory.
Copy.
And this is where we start tweaking Einstein. The source proposes a modified equation, equals mc2 times u log.
Right, so Elie's is the effective energy, the energy in context, and he is defined as the topology factor.
Topology factor. And this is a dimensionless number, right?
Yes, it's a ratio, a multiplier. It doesn't have units like meters or seconds. It's just a scaling factor that adjusts the total.
So let's test this against the gold standard. In boring, empty free space, that asymptotic limit you talked about, what is the value of TTP?
In free space, TT equals exactly 1.
And if TT is 1, then the equation becomes 1 in C2 times 11.
Which is just a Dealey Mp22.
Which is just 1 is preserved. The law holds.
Okay, so Einstein is safe out in the vacuum of deep space. The law of the land holds up where there is no land.
Einstein is safe in the limit, but inside a cavity or between those Casimir plates or in a specific nanostructure, TT is not 1. It deviates. It might be 1.000000001, or it might be 0.9999999, but it is not exactly 1, and that means the energy ledger changes. Now, I want to clarify something here, because there seem to be two different definitions of this factor in the papers, and I got a little confused reading the volumetric rest energy ansatz. They give a definition that looks like it involves velocity. They say TT equals CVT.
Right, and this is where we have to be really careful. The addendum source actually corrects this, or at least it contextualizes it. The definition TT equals CVTT is described as the heuristic definition.
Heuristic meaning, like a rule of thumb, a mental shortcut.
Yeah, exactly. It's the explain it to me like I'm 5 version.
Yeah.
The idea is that $VT represents a circulation parameter. If you imagine the photon or the energy not just moving in a straight line, but swirling around in a confined geometry, like a little whirlpool in a bottle of $V, is the effective speed of that circulation.
So if it's swirling, it's not making forward progress at the speed of light.
Mathematically, the intuition is that if $V, the circulation speed, is less than CLR, then the ratio CVD becomes greater than 1. So the effective energy goes up. It's a way to visualize why constraint increases energy density. You're compressing the circulation.
But the expert source warns us not to take that too literally. We shouldn't actually picture little whirlpools of light spinning around.
Correct. If you lean too hard on that fluid analogy, thinking of light as swirling water, you get into a lot of trouble with other laws of physics, like Lorentz invariance, which we will definitely get to. So the papers provide a hardened definition.
The one that stands up in court.
The hardened definition is purely spectral. It's clean. It says Chan-tite is a ratio of energies. Specifically, you take the bounded spectral energy, you divide it by the reference spectral energy.
So it's just the energy of the choir in the box divided by the energy of the choir in the field.
Exactly. You calculate the sum of all the allowed modes in the cavity. You calculate the sum of the modes that would be there in free space. You divide one by the other. That gives you your factor. This moves the theory away from hand-wavy fluids and into rigorous spectral geometry.
It reinforces that core point. Geometry is never neutral.
That's the key takeaway of this entire deep dive. We have this habit of thinking geometry is just decoration. Oh, the box is a square or a circle, who cares? This theory says the vacuum cares. The vacuum is a spectrum, and the geometry writes that spectrum. If you are inside a nanostructure, you are not in free space. You are in a geometry-conditioned environment.
Okay, I'm with you. Constraints change the choir, which changes the energy.
Hmm.
But I can already hear the physicists in the audience sharpening their pitchforks. I can feel the tension building.
Oh, they're definitely sharpening them. You don't get to modify E equals mc squared without a serious fight.
And to their credit, the authors of these papers know that. They dedicated a massive section in one of them called The Steel Man to basically arguing against themselves.
Which is good science. If you can't destroy your own idea, you shouldn't publish it. You have to be your own worst critic before anyone else gets the chance.
So let's enter section 4, the smackdown. I want to play the role of the angry physics professor here. I'm going to throw these objections at you, and you give me the defense that's provided by the sources.
Let's do it. I'm ready.
Okay. Objection number 1, and this is the big one, relativity, specifically Lorentz invariance. The critique is ratios like energy flow versus density are frame dependent. If I am standing still next to the box, I measure one thing. If I fly past the box at half the speed of light, I measure something else. If your team factor changes based on how fast I'm moving, then it's subjective garbage. Physics is supposed to be true for everyone, regardless of their speed.
This is the most common knee-jerk objection. It sounds devastating. It really does. But the TAFES is actually very simple and grounding. The takedown is bounded systems have a rest frame.
Explain that. What does it mean for a system to have a rest frame?
Okay, look. Consider the room we're sitting in. It has a temperature. Let's say it's 20 degrees Celsius. Temperature is a measure of the average speed of air molecules bouncing around, right?
Right.
Now imagine a spaceship flies through this room at 99% the speed of light. To the pilot of that ship, because of relativity, time is dilated, length is contracted. The air molecules will look like they're moving completely differently. The pilot will measure a totally different temperature.
Okay, so does that mean the temperature of the room is fake? Does that mean thermodynamics is broken?
Of course not. Temperature is a real physical property, but it is defined in the rest frame of the gas. The room isn't moving relative to itself. The box provides the coordinate system.
I see where you're going. The box itself defines the here.
The Casimir plates are physical objects. The cavity is a physical box. It defines a frame of reference. This theory explicitly applies to boundary-conditioned physics. It doesn't claim to replace relativity in deep, empty space where there are no boundaries. It says, hey, when you build a box, the physics inside the box relates to the box. That's almost tautological when you say it like that.
So it's not breaking symmetry. It's acknowledging that the box already broke the symmetry by existing.
Perfectly put. The boundary conditions break the symmetry of empty space. That's not a bug in the theory. It's the entire feature. You can't have a boundary without defining a here and a there. So the objection that it depends on the frame is true, but it's irrelevant because the box provides the one frame that matters.
Okay, round 2. Objection number 2. Standing waves.
Yes. The zero flux problem. I was waiting for this one.
The critique here is, in a standing wave, like a plucked guitar string, the energy vibrates up and down, but it doesn't travel left or right. The net flow, or flux, is 0. If your math relies on a flow velocity, like that $v we mentioned, and the flow is 0, you are dividing by 0. The equation blows up to infinity. Your theory is broken.
This is a totally valid critique of the heuristic definition, that fluid version we talked about earlier. If you try to model a standing wave as a flowing river, the math fails spectacularly. A river goes somewhere, a guitar string just hums in place.
So if you use the simple fluid math on a guitar string, you get nonsense.
Exactly. But this objection fails completely against the Harden definition. It doesn't even land a punch.
And why is that?
Because the Harden definition uses mode density, not flow velocity. It counts the energy of the vibration itself. Even if a wave is standing still like that guitar string, it still exists. It still has a frequency. It still takes up space in the choir.
So the note is still being sung, even if the singer isn't walking across the stage.
That is a perfect analogy. The spectral definition just counts the notes. It doesn't care if they're traveling waves or standing waves. So the standing wave objection is attacking a straw man. It's attacking the intuition pump, the fluid model, not the actual spectral math.
Got it. Okay, objection number 3, and this one feels big. The fifth force.
This is the scary one. This is the one that gets papers rejected from journals without a second read.
Right. If mass changes based on where it is, if an object's effective mass is different inside a box than outside, that sounds like a fifth force. We have gravity, electromagnetism, strong nuclear, weak nuclear. If there was a fifth one, wouldn't we have seen it by now? Wouldn't a feather and a hammer fall at different rates if they were inside some kind of magic box?
The critique is that this would violate the equivalence principle, one of the pillars of general relativity.
So what's the defense? How do they get out of this one?
Scope discipline.
Scope discipline. That sounds like corporate speak for, we'll ignore that problem.
It does, but it's crucial here. It means knowing where your theory applies and where it doesn't. The theory doesn't claim this is a universal field acting on everything everywhere like gravity. It is strictly for engineered topologies.
So only in very specific, tiny, man-made structures, tiny cavities, metamaterials, nanotech.
Right. In normal space, where we do gravity tests, where we drop apples or hammers, cheater is effectively 1. The walls are kilometers away, or light years away. The effect is so vanishingly small, it's not even a rounding error. You only see it when you create the specific geometry to amplify it.
So it's like saying, sound works differently inside an echo chamber, and the critic says, but I don't hear echoes when I'm standing in an open field. And you say, yeah, because it's an open field.
Exactly. You have to build the echo chamber to test the echo. The fifth force isn't missing. It's just dormant until you build the structure that wakes it up. It's not a universal force, it's a contextual effect.
Okay, last one. Objection number 4. Particle accelerators.
The Large Hadron Collider, the big guns.
Right. We smash atoms together at nearly the speed of light. We have tested special relativity to incredible precision. The math works perfectly. E equals mc squared works perfectly. If this theory was real, wouldn't the LHC have noticed a deviation? Wouldn't all their graphs be wrong?
This is the classic we would have seen it by now argument. And the takedown here is fascinating. It's not about the physics, it's about design intent.
Design intent, what does that mean?
Think about how a particle accelerator is actually built. They use these massive wide beam pipes. They pump out every single molecule of air to create an ultra-high vacuum. They use powerful magnetic fields to keep the particle beam perfectly centered as far away from the walls of the pipe as physically possible. Why do they do all that?
To stop the walls from interfering with the beam, to stop the particles from crashing into the sides.
Exactly. They are designed from the ground up to avoid boundary effects. They are designed to be the closest possible approximation of free space that we can build here on Earth.
So they are designed to ensure chi equals 1.
Precisely. So pointing at an accelerator and saying it proves Einstein is correct, but it only confirms the limit where boundaries don't matter. It proves that in free space, Einstein is right. It doesn't test the regime where boundaries do matter, like inside a nanoscale cavity.
So we built a machine specifically to simulate the empty universe, and we were surprised to find it acts like the empty universe.
You can't use a machine that was designed to ignore boundaries to disprove a theory that is entirely about boundaries. It's a classic selection bias in the experiment itself.
That is surprisingly illogical. It seems like the smackdown holds up pretty well, at least on a logical level.
It holds up because the theory is modest. It's not trying to rewrite the laws of the entire universe. It's just trying to refine the accounting for very specific engineered environments.
But as we always say on this show, a thesis without predictions is just philosophy. We need to be able to test this. If it's real, we should be able to go into a lab and measure it. We shouldn't just talk about it.
And that brings us to section 5, the predictions, where the rubber meets the road. This is where it gets exciting.
The sources outline a few specific falsifiable predictions. What's the first one?
Geometry-dependent Casimir amplification.
That sounds technical. Break it down for us.
Okay. Standard Casimir physics says the force between two plates depends primarily on the distance between them. You bring the plates closer, the force gets stronger. The formula is dominated by the gap distance, which we call $.
Right. Distance is the key variable.
This theory says. Now, it also depends on the shape, on the topology. If you have, say, a toroidal cavity, a donut shape, versus two simple flat plates, even if the gap distance $, is the exact same in both setups, the force you measure should be different.
Why? Why would a donut be different?
Because the choir sings differently in a donut. The allowed modes that can exist wrapped around the ring are mathematically different than the modes that can exist between two flat walls. The topology changes the spectrum, which changes the energy, which changes the force.
And standard physics would say it depends only on the distance.
Standard approximations often simplify the topology and just look at the gap. They treat the shape as a minor correction. This theory says the shape is a primary factor. It says if you measure carefully, and we have the technology with things like atomic force microscopes to do this now, you will see a deviation that matches the topology factor, the tree sword of the donut.
Okay, that's testable. What's prediction number 2?
Corrugated plates.
This one is cool. Imagine the Casimir plates aren't perfectly smooth, but they have ridges etched into them, like a Ruffles potato chip.
Okay, ruffle chip plates. I'm getting hungry again.
The claim is that if you systematically change the size of those ridges, the spacing and the depth, you won't just see a smooth change in the Casimir force, you will see non-monotonic deviations. Meaning the graph of force versus ridge size goes up and down. It wiggles.
Yeah, it won't just scale smoothly. You'll get resonance effects. When the ridges are spaced just right, they might match the wavelength of certain vacuum modes, and you could get a sudden spike or a sudden drop in the force.
Because the ridges are actively tuning the vacuum, like the frets on a guitar neck.
Exactly. They are amplifying certain notes in the choir and suppressing others. Standard Casimir formulas usually treat surface roughness as a generic correction factor. This theory treats it as a spectral tuning knob you can turn.
That's a huge difference. What's prediction number 3?
High-Q resonators. This one involves atoms directly. If you take a single atom, which acts like a tiny antenna, and you put it inside what's called a photonic band gap structure.
Which is basically a perfect hall of mirrors for specific colors of light, right?
Right, a crystal structure that literally forbids certain light frequencies from existing inside it. If you put an excited atom in there, its emission rates, how fast it spits out a photon to relax, should change in a predictable way.
Because the photon it wants to spit out doesn't fit in the room. The room is dark at that frequency.
Exactly. The local vacuum energy density is modified by the cavity. The atom feels the room before it even emits the photon. If the room is dark at that frequency, the atom literally cannot emit. This is a known phenomenon called the Purcell effect. But this theory predicts specific, calculable shifts in the atom's energy levels and behavior based on the chiffy of that specific geometry.
And here's the kicker. The source material lays it on the line regarding falsification. They don't head shear.
No, they don't, they say. If we go to the lab, we build these donuts and these ruffle chips, and we measure the force, and we find that it depends only on distance. If the shape and topology don't matter at all, then the theory is dead. Finished.
The model is rigid. It can be broken. I have so much respect for that. It's not moving the goalpost. It's putting your cards on the table.
That's the hallmark of real science. It has to be able to fail. If a theory can't fail, it's not science, it's religion.
Now, I want to step back to the math for a second, to section 6, because there was one equation in the volumetric source that really caught my eye. We talked about it briefly earlier, but I want to drill down on it. T dollars equals MC3 VT2.
Ah, yes. The provocative one.
Yeah.
The one that makes people do a double take.
It just looks wrong. I mean, C cubed, Einstein is C squared. C cubed sounds like science fiction. It sounds like whoop factor 9. Why on earth are we cubing the speed of light?
But look at the units. Let's do a sanity check. You are dividing CD3 trenadol, which is velocity cubed, by Ward-Vollers, which is also a velocity.
Okay, let's do the algebra. Meters cubed over seconds cubed. Divided by meters over seconds, you cancel one out.
You are left with meters squared over seconds squared, which is velocity squared.
So dimensionally, it works. It has the exact same units as 222. It results in joules when you multiply by mass.
Correct. The math isn't broken. It's dimensionally consistent.
But what does it mean? Why cube it just to divide it back down? Why not just use 222 and be done with it?
It's about conceptual framing. It's about what you're trying to describe. Einstein's 222 comes from a derivation that assumes linear propagation, light moving from point A to point B. Light flying through empty space in a perfectly straight line.
Linear, a bullet train.
Right. But the NSATS, the proposal in this paper, is that CC3VD2 describes volumetric closed circulation.
Circulation. We're back to the whirlpool we mentioned earlier.
Exactly. Think of the photon not just as a point or a line, but as a 3D object. It has electric fields, magnetic fields. They are oscillating orthogonal to each other and to the direction of travel. When you bind that complex object into a topology like a tiny cavity, it's not just going from A to B anymore. It's interacting with the entire volume. It requires a volumetric description.
So Thc3VT2 is the math of the whirlpool, while 2Tau2 is the math of the stream.
That's a beautiful way to put it. The volume matters. And this leads to what the source calls the inversion.
This is the psychological flip, the change in perspective.
Yes. The standard narrative in physics for the last century has been Einstein is fundamental, E equals mc squared is the law. Things like the Casimir effect and cavities are just weird fringe anomalies on the side. Ignore the weird stuff in the corner. Focus on the big, simple equation.
Right. They're treated as an edge case or a correction term.
The inversion says, no, you have it backwards. Spectral structure is fundamental. The choir and the room, or the reality. Einstein's equation is just the zeroth order term. It's the approximation you get when you ignore the boundaries.
So E equals mc squared is the simplified version, the one you use when you don't want to do the hard math of the geometry.
It's the limit, as one of the sources quotes. Einstein is graduated from icon to limit.
That is a bold statement. Graduated from icon to limit. It's respectful, but it definitely puts him in a box. Or I guess it takes him out of the box.
It puts his equation in the specific box labeled unconstrained space, which is a very, very big box, to be fair. It covers most of the known universe. But it doesn't cover everything. And interestingly, the most exciting parts of future technology, nanotech, metamaterials, maybe advanced propulsion, they're all happening inside the constrained box.
Okay, so we've covered the theory, the math, the brutal objections. Now let's talk about the so what. Why should our listener, driving to work or doing the dishes right now, care about some obscure factor called chit-tail?
This is section 7, implications. This is where it gets fun.
If this is true, if we can really engineer the vacuum, what can we actually do with it?
The addendum source speculates on this, and it gets pretty wild. It talks about, and this is a direct quote, engineering the vacuum.
Sounds like pure sci-fi.
It does. But if you can manipulate chit-tail, you can manipulate the local energy density of space-time. That has enormous implications for things like magnetars.
The neutron stars with the ridiculously powerful magnetic fields.
The most powerful in the universe. They can find extreme plasmas and energy in ways we struggle to understand. If you could create a geometry that amplifies the vacuum energy, a high Chimidoc environment, you might be able to stabilize plasmas in ways we currently can't even dream of.
You're thinking about fusion energy.
It's a possibility. In fusion reactors, we spend billions of dollars on magnets to fight against the plasma's desire to explode. What if you could use the vacuum choir itself to help confine the heat, rather than just fighting against it? It's a completely different approach. And then there are high-precision sensors. Imagine building a sensor that is incredibly sensitive because it's tuned to the local vacuum fluctuations. Or even, well, the source hints at effective mass modification.
Changing the mass of an object.
Not changing its God-given mass, but changing its effective inertia. If the energy of a thing is 1 ED is MCD2 and you can build a structure around it that makes it significantly different from 1, the amount of energy required to accelerate that object might change.
That sounds an awful lot like propulsion.
The sources are very, very careful not to say warp drive. They show that scope discipline again. They don't want to be dismissed as cranks. But if you can engineer the energy of the vacuum around an object, you are touching the fabric of reality in a fundamentally new way.
It comes back to that word we keep using, context.
Yes. Physics isn't just about the particle. It's about the particle and the room it's in. We've spent 100 years studying the particle in exquisite detail. Maybe the next 100 years will be about studying the room.
I love that. Study the room. It implies that we have been ignoring half the picture this entire time.
It's humbling, really. It admits that we aren't separate from our environment, even at a quantum level.
So let's wrap this up. We've been on quite a journey today. We started with boiling water on Mount Everest.
Then we went down to the microscopic plates of the Casimir effect.
We talked about the math of Chicken-Uller and the spectral choir.
And we survived the Steelman defense against the critics.
If you had to summarize the central mission of this deep dive in one single sentence, what would it be?
Constraint writes the choir. The choir writes the energy. The ledger depends on the box.
The ledger depends on the box. I'm going to be thinking about that for a while. It's this idea of honest accounting.
That's really what it is. It's not new physics in the sense of finding some magic unknown particle. It's just looking at the books and saying, hey, I think we forgot to count the walls.
And once you finally count the walls, all the numbers change slightly.
The vacuum is real, it is spectral, and it is shaped by geometry. We have to account for it.
I want to leave our listeners with one final thought. We talked about how gravity, how nature creates these constraints. It makes the stars, the planets, the pressure gradients that boil water.
Right, nature builds the first boxes.
But humans, we are tool builders. We are box builders. And now we are starting to build shapes at the nanoscale that have never existed in nature. We're building metamaterials, nanostructures.
Toroidal cavities at the nanoscale. Ruffled plates with precise corrugations.
Exactly. If space isn't just an empty stage, but an active participant defined by its shape. What happens when we start building shapes that the universe has never seen before?
That is the big question, isn't it? Are we writing new laws of physics just by building new boxes?
That is a provocative thought. Are we the architects of the next layer of physics?
I think we might be. We're moving from being observers of the vacuum to architects of the vacuum.
Well, on that note, we're going to let you mull that over. Check out the show notes for links to the source material if you want to dive into the math yourself. But be warned, there is calculus.
Plenty of calculus. But it's worth the wait, I think.
Thanks for listening.
Keep thinking critically.
And keep diving deep.
All right, today we're diving into an idea that, well, it kind of flips everything we think we know about physics on its head. It all comes down to one massive question. What if the shape of space, its geometry, can actually change the fundamental rules of the universe? Yeah, you know this one. E equals mc squared. It's got to be the most famous equation in all of physics, right? It's on t-shirts, it's everywhere. It's Einstein's masterpiece, connecting energy and mass. Simple, elegant, and, well, it's the foundation for so much of what we know. But what if it's not the whole story? What if that perfect, clean little equation is actually an ideal case? The version that only really works in a perfectly empty room and infinitely huge vacuum. So what happens when you take the universe and you put it in a box? Okay, so let's unpack that idea. Is E equals mc squared really the whole story? We're about to see that it's not the final word, not by a long shot. It's more like the starting point for a much bigger and honestly a way more interesting picture. See, that famous formula, it describes what happens in what physicists call free space. No walls, no boundaries, nothing getting in the way. But our universe isn't like that, is it? It's full of constraints, of boundaries. And the second you introduce a boundary, whether it's a box or a planet or even the tiny cavity between atoms, the rules of the game can actually change. Now, to really get a grip on this, let's just forget about the quantum world for a minute. Let's look at something completely down to earth, an example you might have even experienced that shows exactly how this works. Okay, so imagine you're trying to boil some water. At sea level, no problem, it boils at 100 degrees Celsius. We all learned that in school. But now, let's say you're on top of Mount Everest. The pressure is way, way lower up there. And guess what? The water boils at just 70 degrees. So think about that. It's the exact same water, H2O, but it needs a totally different amount of energy to boil. Why is that? Well, it's not because the water molecules changed. They're exactly the same. The only thing that changed was the constraint environment, the box they were in. In this case, the atmospheric pressure, completely rewrote the rulebook for how much energy it takes to get that water boiling. And this brings us to a really cool metaphor from the source material for this whole idea. Think of it like this. The pressure, the bar, is the box. And that box changes the choir. The choir represents all the possible ways the water molecules can vibrate and move around. So by changing the box, you change the choir. And that changes the energy you need. Remember that phrase, the choir. All right, so we get it for boiling water. But how on earth does this connect back to the quantum vacuum? Well, believe it or not, we're about to see the exact same principle, the box changing the choir, play out, just on a mind-bogglingly small subatomic scale. And this isn't just a thought experiment. This is a real, measurable thing called the Casimir effect. It's wild. If you take two metal plates and put them incredibly close together in a perfect vacuum, a mysterious force actually starts pulling them together. And that's our proof. It shows the vacuum isn't empty at all. It's more like a churning, roiling sea of energy fields popping in and out of existence all the time. And this is where that choir metaphor just clicks into place perfectly. Outside the plates, you have the full choir of all possible vacuum energy wavelengths singing away. But inside that tiny gap between the plates, well, the plates act like a box. They filter out some of the notes, some of the wavelengths can't fit. So you're left with a much smaller, quieter choir of energy modes inside. So you've got this difference, right? The loud, full choir on the outside and the quiet, filtered choir on the inside. That creates an energy imbalance, a pressure difference. And that imbalance produces a real physical force pushing the plates together. The geometry, the box, has literally altered the energy of the vacuum itself. How cool is that? Okay, hold on. We've got boiling water on a mountain, and we've got quantum plates in a vacuum. I mean, these seem like two completely different worlds, right? Well, they're not. underneath it all, they share the exact same universal skeleton. And here it is. This is the core logic. It's a simple three-step chain that ties everything together. You always start with a constraint. That could be pressure, it could be geometry, any kind of boundary. That constraint then changes the spectrum. That's our choir of allowed energy states. And finally, that new altered spectrum determines the final energy of the system. Constraints, spectrum, energy. That's it. And just look at how cleanly this maps onto our two examples. For the water, the constraint is atmospheric pressure. For the Casimir effect, it's the plate geometry. In both cases, the spectrum of available energy modes gets changed. And the result? A new boiling point for the water and a measurable force for the plates. It's the exact same law, just working with a different choir. This unifying idea, this universal skeleton, is so powerful that it really deserves its own name. And this is where we get to the absolute heart of it, and we see just how deep this rabbit hole really goes. It's called the spectral constraint principle. And what it says, in a nutshell, is that the way energy shows up in the universe is always conditioned by the geometry of its environment. Think about that. Geometry isn't just some passive background, some stage where physics happens. It's an active player in the game. So how do we actually account for this in the math? Well, we can update Einstein's famous equation. We add something called a topology factor, which we write as chi-t. Just think of it like a little correction knob. It's a number that tells you exactly how much a system's unique geometry is tweaking the energy away from that simple E=mc² ideal. So let's break down this chi-t thing. In that perfect infinite vacuum we started with, chi-t is just equal to 1. 1 times mc² is just mc². So we get Einstein's equation back, no problem. But put yourself in a constrained space, like between those Casimir plates, and chi-t is no longer 1. And here's the key thing to remember. This isn't about proving Einstein wrong. The source material calls it honest accounting. It's about finally giving geometry its proper place on the energy balance sheet. And the ambition of this idea is, well, it's huge, because this principle seems to stretch all the way up to gravity itself. I mean, what is general relativity? It's the idea that the curvature of space-time, which is the ultimate geometric constraint, right, is what bends light and alters the flow of time. That's just another way of saying it's changing the energy of the system. It's the same principle, working on everything from a pot of water to the entire cosmos. So let's end with this thought. We usually think of space as just the container, right? The empty box that holds the universe. But what if it's more than that? What if geometry, the very shape of things, is actually a co-author, helping to write the fundamental rules of physics? It suggests that the box you're in might be just as important as what's inside it.